So the distance that you can generate most often from a vector data set in ArcGIS would be Euclidean distance. Like you're starting from a set of whatever vector feature you're working with, points, lines, or polygons. It creates a grid for you, a raster surface. Each cell represents a particular distance from the feature, the closest feature to the grid cell. So that's why we have these different bands around the roads and with between the roads, representing distance from each of the closest roads. Okay, so and the distances are calculated in whatever the coordinate system map units happen to be. Typically, again, the most common that we use are meters or feet. So they're calculating each of those color bands out there represents a different major distance from the closest road. Euclidean direction. Well, here we go. Here's aspect again. But from the cell to a feature. So instead of creating a true aspect grid that shows the landscape orientation, what this is doing is saying we're feeding the analysis, in this case, a road network, from each cell location, which way is the closest road. Okay, that's what this particular thing is doing. The output is going to look exactly the same value wise as to an aspect grid, but Euclidean direction is saying from each cell location where is the nearest road, which direction is it, and I'm facing that direction. Okay, so it's going to be it's compass direction, but it's compass direction that's determined from the cell location to wherever the nearest road is. So that's different from the landscape aspect, which the landscape is saying the landscape aspect grid is telling you here's where the slope is, and here's how the direction that the slope faces, north, south, east, and west, or anything in between. Okay, so that's the true landscape orientation. This is direction from a cell to the road, measured in degrees. So just be aware of that. Don't choose the wrong thing when you're generating a grid. If you want aspect, this will look like it, but the values are not what you're looking for. So buffers in raster require that you first create a distance grid, and then you select from the distance grid using raster calculator whatever distance you're interested in, which creates a Boolean output of 1 for true, 0 for false. So we're using that logical expression technique to query the grid to produce our buffer in raster data format. Now, if you want a more accurate, precise, and truthful buffer, you're going to use a vector version of the buffer using the geoprocessing tools. However, if your analysis requires a raster input of some kind that is a buffer, then here's a way to do that that is more appropriate for that data set type for using raster data. So you generate distances first, query it, the distance away from the features, in this case is a road network. We want the cells that are less than 500 meters away from the road or 500 feet away from the road. We don't know the units. And so those are true, those are ones shown as blue, and the zeros are false shown as white. Okay, so here's how we can generate buffers or model buffers using raster data. So again, looking at distance, and one of the things that we commonly do with distance information and these other types of information, using inputs of the elevation, slope, distances, and direction, we can calculate a cost raster for cost analysis for the least expensive way to get from point A to point B, or the fastest way to get from point A to point B, You can do that, do that analysis and generate an output that's the amount of time it gets from location to location, or perhaps the true cost in money for miles per gallon for a vehicle that it takes to get from point A to point B, those kind of things. And so that's generally called the least cost or lowest cost path kind of analysis. And so it uses some concepts from the network data model and raster data to generate that kind of information. So it's an example of how we can use rasters to first create all these different outputs that are in themselves analyzing the terrain, and then combine them together into something that solves a particular problem. In this case, how much time does it take to get from between those two locations? What's the easiest path between those two locations? Is another way to think about it. It may be that the person is trying to analyze the easiest way to get, using the example from before, a tank from the more brown dot to the pink dot, and this is the best path that they could take, the least cost path, the one that's going to involve the least amount of stress on the engine. Perhaps it'll use the least amount of fuel to get between those two locations. It could be the fastest route possible between those locations. That's what you can use this type of analysis to calculate. Well, now we're going to switch gears and look at a different kind of a surface, the triangulated irregular network. This is something that can be derived from DEMs. It is not a DEM. It has its own characteristics and its own special way of mathematically describing surfaces. So it is a complete surface. It doesn't have any breaks. It completely represents the landscape, but it does it in a very different way. The way that TINs, as we call them by acronym, the triangulated irregular network, sometimes called a triangulated interpolated network, derived from a DEM, is described or modeled by points, lines, which are known as edges, and then polygons that are known as facets that happen to be triangles. So these triangles, each one represents elevation, it represents aspect, it represents slope. Okay, so this makes it a very different kind of a representation of terrain than a DEM, which is this regularized grid of square polygons or pixels across space. So this is an irregular network of triangles that is describing, think of it as describing the peaks and the valleys, as a DEM would do it using those squares and elevation values. This is using triangles to describe the changes in elevation and the morphology of the landscape. And how this works is based upon a particular mathematical technique called Delaunay triangulation. Delaunay triangulation requires that each triangle can be circumscribed by one circle, and that circle will intersect 3 points and 3 points only. So it has to contain only 3 points on its perimeter. It cannot contain more than that within itself. So the circle, each circle here, is connected to only 3 locations, 3-point locations. If it contains 4-point locations, as the one on the kind of the lower left is doing, then it's an unacceptable circle. It's got 1 point too many. Something has to happen. And so we're going to modify the formation of the triangles that are described by those 3-point locations on the perimeter of the circle in order to get that errant point into a circle set with 2 other points. Okay, so this is a really complex thing to take a look at, but what it's trying to do is to show, given a sample of points in an array, and those points are elevation values, think of them that way perhaps, that are drawn off the DEM. So they're sampled off the DEM. You've got these points that are showing high and low values, and then we're trying to describe all of the possible combinations of 3 points that can be used to create a circle. So this is what's happening in the background when you call up the tool to form and create a DE or create a tin from a DEM. It's drawing sample point locations from the DEM and then using that information to generate these different triangular facets, the points, edges, and the facets of the triangles that simultaneously are going to be giving us information about elevation, slope, and aspect of that facet, as if it was something that you could fit a triangle to the landscape. So it's doing all 3 of those things simultaneously. And so what's happening here, this diagram is showing us in principle what the Delaunay triangulation does for these polygons described by points A, D, C, and B in the interior angles of those. The sums of alpha and gamma, A and C, must be less than or equal to 180 degrees. With circumcircles describing them, describing the triangles, must contain only 3 points. In this particular case, both circumcircles that were originally drawn will contain 4. And that's not acceptable under the rules for this particular transformation. So what happens is that we break apart the triangles and we redraw the boundary between them, the shared adjacent line between the 2 triangles, so that then we can circumscribe each 3 points with a single circle. So that's what's happening here in the diagram up on the top. We're running from that really simple set of points. Initially, the algorithm says, well, I'm going to draw points here, I'm going to draw lines, create edges here, here, and here, and here. But then I've violated the rules for the transformation, so that's not going to work. So we're going to go back, break that thing apart, draw it again, and then we're going to wind up with facets that match what's on the far right. The one in the middle is after the initial creation. It says, well, no, this isn't going to work. I'm going to have to do this instead. And so that's kind of what the process is doing without going deep into the math behind it all. So the result that you see when you generate a tin, when you use that tool, is going through this process. It's sampling point locations. It's trying to draw these triangular facets between them, and it may discard points in order to create the most efficient triangular representation of the landscape that is maximizing the minimum of the angles, of the interior angles of these triangles. So that's it's trying to optimize that. So the end result, what we see, there's a lot of calculations that go on that get discarded that we don't find in the final product. Is kind of what the whole point of this slide is that the algorithm is analyzing, it's making determinations, it does things and says, well, no, this doesn't work, we have to fix it, so here's how we fix it, and then we get the final output from that, which is the triangulated irregular network. So now we've generated a tin, Here's a graphic sample representing a tin with those points, edges, and facets. And by itself, it doesn't really look like it means anything. It's hard to interpret what's happening there. This looks like a jungle gym thing from back in the last century. Maybe this is something kids hang on and play with, right? And who knows what this thing is? It's really hard to interpret one of these outputs if there's no coloration. But if we add coloration in to these facets, and then we're showing a little bit of those facets through them, now we can kind of get an idea of what's happening. So imagine that this particular tin was generated to describe a DEM of a landscape. And here we have an example of a mountain. And we're looking down at the mountain on the right, looking down at the peak, which is colored in white, as it traditionally is for the high alpine areas. And then we're scaling down into different color shades that represent different elevation values as we're moving lower and lower in elevation away from the mountain peak. And at the same time, we're seeing all these triangles that are describing what does that landscape kind of look like. So it's a mountain. We're using triangles to model the mountain slope. The mountain changes in elevation, the direction that it faces, its aspect. So here, when you do this kind of output and you create it, you're going to have a visual output that's really easy to interpret compared to this lattice structure underneath it, the framework of the points, edges, and facets with no coloration. That really is not terribly useful except for geometric analysis. But for the visual analysis, we need to apply colors to the different elevation ranges, and that helps us really interpret what this tin is trying to show us, what it's modeling on the terrain. So think of it maybe another way would be here you've got a mountain, and on top of it you drape a blanket, but the blanket is going to follow these triangles and wind up being that kind of a configuration. It's just draped on top of things. It's very geometrical instead of being very smooth. Okay. So here, this is what your output generally looks like on the right, except that the framework typically is invisible. So some modifications that we can make to the tins to make them a little bit more realistic and is to add things like mass points and break lines. So mass points are point locations where we have elevation or height measurements. And below that, we see here's what the original tin output looks like. Okay. Now we're going to bring in break lines, which are vector lines describing areas and features on the landscape, but they don't necessarily have any height measurements or elevations attached to them, but they are features on the landscape. So we can pull both of these things in, these mass points or these break lines, and we can say, well, take the tin and make it look more like it does in reality. So what this is, here's a neighborhood that has different parcels, different pieces of property, and that have been flattened out in order to receive the houses that are probably on them, the streets that exist between them, and the sidewalks and the driveways. So we're using the mass points and break lines of elevation values and then just geometric features that exist on the landscape to make the tin more closely represent what it actually looks like. So here's a neighborhood at the foothills of a mountain. All right, so it's just a way that we can modify a raw tin and make it more useful for our analysis if we need to take into account what's actually out there. And the tin itself may not be able to represent that. If the tin is based upon straight elevation values, which are just the land surface, or if it's an area maybe that was when the DEM was created, it was more of a natural area that got turned into a subdivision. And so afterwards, The DEM has changed a little bit, but the DEM alone really isn't going to be able to capture the details that exist in the things like the sidewalks, things like modifying for parcels. Okay, our cut and fill operation isn't going to be able to get that in that amount of detail, most likely. So here's again a way that we can modify a tin output to more closely model what is on the terrain, especially in human modified terrain.